more or less education, more, if you have 5 more education, less education. There's no difference between people who have a lot of education and not too much education in their mean income. That would be a T-test. Okay? You can hear the term difference in the apostles. This is saying the more you get of one, the more you get of another. Okay? That doesn't always have to go in that kind of a direction. Because it is a directional hypothesis. I'm not saying that there's no correlation between education and income. That would be a non-directional hypothesis. I'm feeling a direction. The more an education you get, the more income you're going to make. So it's a directional hypothesis that's on the table here. It doesn't have to go in that direction. Take the relationship between education and how many children you want. Typically, the more education you get, the fewer children you want. And so that is a directional hypothesis, but it's going in an opposite direction. And we'll talk about what that implies about the region of rejection in just a moment. But still, the same logic is being, you're looking at the same thing for this test of correlation in terms of direction, in terms of whether it's a one-tailed or two-tailed test. We'll get there in a moment. So it is the RI. RI, you apply the central limit theorem, it's going to produce a normal distribution scores. The value that occurs most often is going to be 0. There are going to be positive values on this side, just like in the T, or positive and negative values on this side. The difference between R and T is the highest value you can get out here is going to be a 1.0. And the highest value you can get on the negative direction is a negative 1.0. It cannot go beyond that. So if you get a correlation and it's a 1.12 or 1.42, something is going wrong because correlation cannot go over 1. Okay? All right. So there's my R distribution. Now, that's the distribution that I'm choosing. Second decision is what is the level of significance. Let's say we want to test it at 105 or okay. So third decision is what's my region of rejection.
Wait, can you go to that decision again?
Again, I'm not saying anything. So we understand it's the minimal conventionally accepted alpha, which is 105. And so the third decision is what is the region of rejection. And there we need a table again. We need the table and on those tables that I sent you. It should be the last page in that set of tables. Here's our correlation. So now let's read that table. You can see one of the first things it's asking for is degrees of freedom. Okay? So along that first column, it says degrees of freedom. Degrees of freedom for R is going to be minus 2. Okay?
What is the table?
It's the very end.
So that's correlation between freedom?
You talking about graphs?
Alright. So the degrees of freedom for R is n minus 2. So I have actually a data word it. So let's pick the data on the word for it. Let's say that we collected this data. We got 4 people in our sample, and let's say we asked them how much education they have, and first person tells us it's got one year of education. Y is income. This is dollars per hour. And so this first person says that they're making $8 an hour. Second person in the sample has 2 years of education, and they're making $7 an hour. 3 years of education, and they're making $84.
The correlation is going to be concerned about, as I increase in values, I purposely put this in order for our first one to see that this thing is increasing. Is this thing increasing or decreasing? Because that's what correlation is designed to try to tap. And you can see that we're probably not going to expect too much of a relationship here because it goes up, it starts at 8, comes down, goes back up, comes back down.
The numbers represent money.
These are dollars per hour, this is what they're making per hour. And so we have a very small sample. We wouldn't want to do this in real life with this small sample, but so I can move through the procedures pretty easily. We'll keep it small. Okay? So, there's only 4 people in this sample, and I have 2 pieces of information on them. Unlike in the t-test, I had, when we have the problem I just worked, I had 4 people who, or 1 group and 4 people in another group. This, I only have 4 people, and I have 2 pieces of information on each one. So n is 4 minus 2, which is 2. There are 2 degrees of freedom. Now I'm looking to see what the critical value is here on this distribution. So I need to move over from that 2 to see what is the critical R value. And as you move over, you see very much like a t-test, a tier that says for 1 tail or a tier that says for 2 tail test. Okay? Now, we have a hypothesis that is directional. The directional hypothesis calls for a 1 tail test. And so I'm going to be using that tier that's headed up 1 tail. And we said that we don't think it's 105. So it's a 1 tail test and it's going to be at the 105 level. The question is which tail are it in? If you look at this hypothesis, the research hypothesis, I think the higher you are on 1 on X, then the higher you're going to be on Y. If that's the kind of direction you're thinking, it's going to be positive. Okay? So the more education you get, the more income you'll make. Or conversely, the less education you get, the less income you'll make. It doesn't matter how you say it. It's going to be a positive. So here's the positives. Negative is on this end. The critical value is on the right side. And the question is, what is the R? What is the critical R that falls there? And that is 0.900. Now, let me say this about direction. If it was that other hypothesis that I looked at to talk about that more education you get, the number of children you want, more. So the hypothesis was the more education you get, the fewer children that you want. Of course, we have to test the null.
I'm sorry. So say if it was the less education you have, the less money you make, is it still possible?
Right, same thing. But we had moved ahead to talk about the alternative hypothesis, but another hypothesis might be that the more education you have, the fewer children you want. Here's a situation where the higher you are on the independent variable, that's education, the lower you are, you're expected to be on the dependent variable, the number of children that you want. When you have this kind of a situation, you're expecting it to be a negative. You're expecting the R that you get to be on the negative side. So if that's the nature of the direction, the critical area would be on the left side.
Okay. So in order to have a negative, the independent variable is going up and the dependent variable is going down.
You're expecting that, it should go either way, that you're expecting this variable to go up, and you're expecting an opposite direction, as opposed to the positive direction, so they're both moving in the same direction.
Alright.
So, we have our critical value, we're ready to work the problem. All we got to do is now is work the observed arc of this data and plug it into these four decisions that have been made here, and we have our answer to either accept or reject the null hypothesis. Correlation, R is a symbol that's used for correlation, and here, many times we put a subscript that gives correlation between X and Y. We understand X is years of education, and Y is dollars per hour. And, let me give you a logical formula for this. This is not the formula that you can work to show you what correlation is. And that is that it is a ratio of the covariance between two variables to the variance in each one of those variables. So we've seen what the variance in variables looks like. That is for X, how does X differ from the mean, square those differences, and sum the values.
You write this formula down or you just do it?
This is a logical formula. So that when I do write my real formula, the calculating formula, it makes more sense. And we can the variance of Y, we do the same thing. How does each of Y differ from the mean of Y? Square to get rid of the negatives, and something like that. So we multiply those two values together. And it's another radical. And then covariance is a term that we have not had yet. That's found when two variables covariate together. And that would be the sum of
What is that, RX4?
X's minus 16.
What did you say covariance?
No, I can't see that.
What's the covariance again?
Covariance is how the two variables are covariant together. This is something we've not had. We can look at the variance of it, but not the covariance. And that's how does each X differ from its mean times how each Y is different from its mean. And I'm going to sum up the values.
So that's the formula?
No. This correlation is a measure of the covariance between X and Y to the variance in X times the variance in Y. The logical formula that reflects that, and this is the one that we're going to work, is that, and here we're going to work with just the raw scores, N times the sum of X, Y, minus the sum of X times the sum of Y, divided by the square root.
The sum of X,
What the?
the sum of X,
I think you've had.
We're going to raw scores N times the sum of X, Y, minus the sum of X times the sum of Y.
That's the That's the
This is the one we're going to calculate.
N times the sum of X minus the sum of X times the sum.
And now the variance for we're going to do 1 for X, we're going to do 1 for Y. This is all on the right. This denominator is all on the right. So that would be N times the sum of X squared minus the sum of X squared. N times the sum of X squared minus the sum of X squared. You do the same thing for Y. Okay, N times the sum of Y squared minus the sum of Y in parentheses squared. Okay. This is the formula your author has. This logically is what it is. but you can't necessarily see variance. Remember, variance is the average amount by which each score is different from the mean. You can see that here. Summing up, now, we are not dividing by units, so we're not calculating an average, but this is called a sum of squares. But you can't see the variance in X, the variance in Y, and you can see the covariance in terms of cost of multiplying two variables. Okay. Alright, so we're not gonna, I wanted you to see that, but don't worry about this thing right here. Here's the Alright, let's
Maybe every time. Nah, this is over.